Okay. All right, we are going to finish up stress transformations today. Got 2 final examples, okay? Hopefully these have been helpful to you. I think repetition helps with Moore's circle. It can be kind of confusing, some of the principles behind the fact that Moore's circle is twice the angle that's in the real world, right? The principle that we potentially have this maximum stress that's greater than the stress that we calculate based on, say, normal stress or torsional shear stress, right? That we can cut an element at a different angle than just perpendicular to our, say, the axis of a steel rod. And we're going to have stresses that are in larger magnitude, right? But we need to look at that for design to make sure that we're considering all possible orientations, right, of stress within our object to make sure that we capture the maximum stresses that the object's going to see so that we can design our element appropriately, right? I guess quickly, we have a homework. It's due Friday, right, at midnight. Don't forget that. We have quiz also, right, this week. It's going to be on Moore's circle. Okay. So, second to last example here. Again, similar to some of the other examples where we are given an initial stress state, okay? So we're given that we have an orientation of a block, right? Piece of our material or an element. It could be a small block of a plastic rod like this, right? And it's oriented such that this plastic rod has a torsional shear stress on it, right? 25 megapascals, so you could assume if it was part of this rod that it has torque on it. And also it's under compression, right? So we got this compressive load sitting on top of this pipe also, plastic pipe. And so we get a stress state that looks like this, and they ask us to draw a Moore's circle for the stress state, determine what our principal stresses, maximum in-plane shear stresses, right? Those are some of the most critical parts of the whole puzzle, right? Those are our maximum stresses that we're going to see both for normal stress and shear stress that we can then go back and relate back to allowable stresses. Then they want to show these on an appropriate sketch, right? So we take it off of Moore's circle and we look at what does that look like in the real world, right? If we had to slice this plastic pipe, okay? So in this case, this stress block is as if we had a compressive force on the top of this plastic pipe, right? And we were twisting it at the same time. And we looked at the stresses by just cutting a piece off of this column, right? We just cut it off and we were looking at the edges of this column. We would have a shear stress and a normal stress like we do. Well, those principal stresses and our maximum shear stress are going to be at a different orientation, right? It's not going to be at cutting this perpendicular to the axis. We're going to cut it at some angle. And when we cut it at some angle, the stresses that are normal to that surface are going to be higher, and we need to know those. And so we draw those orientations too, because as we know, Moore's circle, the rotations that we do in Moore's circle are twice that what we do in the real world too. Okay, so we drew Moore's circle based on our coordinates. These coordinates come from our initial stress state, right? The 45 and the 25. Based on the sign convention of Moore's circle, right? Clockwise above the x-axis, counterclockwise below for shear stress, tension to the right, compression to the left for normal stress. Then based on having those 2 coordinates, we can draw a circle knowing that the center lies at the average normal stress, right? Halfway between our x-coordinate and our y-coordinate. In our case, it's negative 22.5 megapascals. And then based on that, we can come back and figure out our radius too, right? We use that equation a lot. It's essentially using the Pythagorean theorem, knowing that we have a given leg, right? One leg is going to be our shear stress based on the coordinate of our, say, x space. And then we have our our normal stress, right? So we can get the 2 legs of that triangle, square them and then square root them. We get a radius. We got 33.63 megapascals. So we asked for the principal stresses and the maximum in-plane shear stresses. Well, we know principal stresses are our 2 points on our x-axis, right? We'll have sigma P1, sigma P2. right? And these are our maximum and minimum stresses. And to get there, we take our initial stress state, right? These are our two coordinates, our x face and our y face. And we need to rotate our block, right? To orient the faces of our block so that we get these principal stresses. So in order to do that, we rotate usually an angle called alpha. And we use the inverse sine, or inverse tangent, sorry. Inverse tangent. In this case, it's 25 over 22.5, right? Opposite over adjacent. This being opposite, and this leg being adjacent. Right? The opposite leg is essentially the y coordinate for our x point for 25. And then our adjacent leg is really the coordinate for our center, right? Coming from 0. So we get this 25 over 22.5. Or we get an alpha equal to 48 inches, or 48 inches, what am I doing? 48 degrees. That means our actual angle of rotation in the real world is half of that, right? So 24 degrees. So that would give us our orientation. We want to know our magnitudes, right? And our sigma max and our sigma min, or our two principal stresses, are really the center point plus and minus our radius, right? So we start with sigma P1, or our maximum stress. It's going to be the center plus the radius. In this case, we know the center is at negative 22.5 megapascals. We're going to add the radius, which is 33.63. And we get 11.1 megapascals. Sigma P2, or our second principal stress, which is our minimum stress. We have the center minus the radius. So negative 22.5 minus 33.63. And we get a principal stress, second principal stress, or minimum stress, of negative 56.1 megapascals. So now we've got our stresses, right? We've got our maximum principal, or our principal stresses, which are our maximum normal stresses. We know that our maximum in-plane shear stress is the radius, right? It's just the radius of this circle, because the maximum shear stress acts above and below the center, which you're going to be a magnitude of the radius away from. We know the radius is 33.6 megapascals. So we've got our critical stresses, right? Maximum normal stresses, both in compression and tension, and then our shear stress. So they asked us to indicate these stresses on a sketch. So you start out with our, initial stress state, where we have, based on the problem statement, we have figured this out already. Right, we had shear stress of 25 megapascals. We had a compressive stress acting on the y face, right? This was the y, x. That's how we got our coordinates, were our values at each of these faces, right? The x faces and the y faces. So we have our initial orientation. Well, based on Moore's circle, right? We figured out alpha, that would be our rotation angle to our principal stresses. It's clockwise, right? We're rotating from our known state, which we have our two coordinates. We drew our line. in order to get to our principal stresses, we're going to rotate clockwise that alpha, but in the real world, it's really half of that, right? Did you really just yawn in front of me? Man, it hurts. Right? We decided that was 24 degrees, right? So we had to rotate our stress block 24 degrees. Right? We can indicate now our stresses on this new oriented block, right? We rotated 24 degrees to get our principal stresses. So now if we look at our XY faces of our block rotated, it really looks something like XY, like so, right? So this is just a housekeeping exercise at this point, right? We're just trying to track our faces of this block. So we had our initial orientation, we rotated it clockwise, our X face, right, is now this X face. Well, if we look at our coordinates, our original X face was there, we rotated down, so now our X face is now this sigma P1, right, is our maximum principal stress, or we know that it's a positive 11.1 megapascals look at something like that, right? It's in tension. Similarly, if we go back to our Moore's circle here, right? We had our Y coordinate, which was our stresses on our Y face originally. We rotate 24 degrees down to our sigma P2, right? So our sigma P2 is the stresses that are going to be acting on this new Y face that's oriented at 24 degrees, which we knew was 56.1 megapascals, right? It's in compression, it's negative, okay? No shear stresses on this stress block, right? Because our principal stresses are where we do not have any shear stress. So something to think about here though, a way of depicting now, which we did in the previous example, which you'll do on your homework, is a way to depict the principal stresses as well as our shear stresses is by merely showing a plane that's oriented 45 degrees from our orientation that we have now, right? So if we cut a plane across here, right? We get rid of these. Because if we have half of this square, right, we know what the principal stresses are. We're going to have maximum principal stress of 11.1 megapascals, minimum or a sigma P2, 56.1. Okay, and if we cut, oh shit, that's not what I wanted. If we cut through this stress block at 45 degrees, all we're effectively doing is saying we're going to take this Y face, right, and we're going to rotate it up 45 degrees, right, counterclockwise 45 degrees. What does that mean? Well, if we look at our original orientation, we had X and Y points, right? These are our faces of our stress block. We rotated clockwise to get to our principal stresses. And now we're actually rotating back counterclockwise 45 degrees, which is 90 degrees on this circle, right? So we can just go boom to here, we get our principal stresses, we show them on our stress block, then we cut our stress block at a 45, which is essentially showing us a surface that's at a 90-degree orientation on Moore's circle, which gives us our maximum in-plane shear stress, right? So if we track this, our Y face started out, right, with 45 and 25. That's this coordinate here. We rotated clockwise our 24 degrees. Now our Y face is this bottom point here, right, 56.1, which is our sigma P2, which is on the side. Okay. Now we're taking this stress block and we're pulling that Y face up, right? That Y face is now 45 degrees up. So if we go clockwise and then counterclockwise, we're down into this point, right? So we're gonna go zoom up here, and then we're gonna come back down. Right? So if we look at our maximum shear stress, which is our radius, 33.6 megapascals, well, that's the magnitude, and we also have a direction, right? If this point is down here below the x-axis, we know it's counterclockwise. So it's going to want to spin the face of that counterclockwise, right? So now we could then just draw a shear that is 33.6 megapascals. This coordinate, though, also has a normal stress, right? It's not sitting on the y-axis. It's sitting off to the left, so we know that it's got a compressive normal stress on it. Well, that coordinate is the coordinate to the center, right? It's directly below the center. So our x-coordinate for the center is 22.5, so we're going to have this 22.5 megapascal compressive stress acting on that face, okay?
And some of the homework ones referring to the drawing shown in
These are the drawings. Yeah, it's this one, and we did it for the example before this as well. It's a way of packing in the principal stresses and the maximum in-plane shear stresses all in the same diagram. If you read the book, John was showing me earlier today, the book does it this way, and they also do it where you could rotate 24 degrees, right? Draw your full stress block, and then if you went back to this original stress state, you would be rotating down, right, to our tau max, and which would be 24 plus would be 21 to get to 45 degrees between these. And so you'd have a stress block up here, and it would just be showing you the same stuff. Any questions? Okay. All right, last bit of this is to try and pull it together from a design standpoint, okay? When we first started talking about this, we were talking about combined loading, and for you CETs, super lucky people, right? We talked about this idea of a drill, right? And that drill is going to have some axial load, right? We're trying to push it into the earth while twisting, right? We're essentially drilling into the earth. So it's going to have axial load. You METs, right? We deal with a propeller. We look at a prop, and because it is right, pushing or pulling on the water, right, the fluid, to either propel the ship or vessel forward or backward, right? We impose this axial load. In order to get the axial load, we have to impose a torque, right? Which comes from a motor that has power in it. You guys could come from power all the way back to figuring out what the forces are and the shear stress in the shaft, right? So we have this normal stress and a shear stress. Sigma is based on the force over the area. Tau is based on the torque times the max radius over the polar moment of inertia, right? So you guys are mumbling those equations in your sleep. Aren't you? No? Right? So if we had a drill stem or a propeller shaft, okay, and we decided to make it out of, let's use A36 steel. Anyone know what the yield stress is for A36 steel? Take a wild guess. I guess that was a wild guess. I'll give you that. Take another guess.
I didn't even think about that one.
Take another guess based on A36.
Oh, 36,000.
There it is. 36,000 KSI, okay? You beat me to it. You would have gotten it right off the get-go. Okay. A36, yield stress for A36 steel, which is it's called mild steel. It's what a lot of plate steel is made out of, typically channels, angles. If you go to Pacific Midwest and you got something that's made out of those components, most of it is made out of A36 steel, okay? Very common. It has a yield, but as we talked about with our tensile test, right? There's an ultimate capacity as well. The ultimate stress for A36 steel typically hovers around 58 KSI. And all these are based on ASTM, right? In order to be designated as A36 steel, they give you limits on the materials that are in it, how much iron, nickel potentially, carbon, all of that stuff, how well it tests within like the range of yield, right? You at least have to be 36. They don't want it to be 100 either. Our shear yield stress is usually 21.6 KSI. It's usually about 0.6 times the yield stress or normal yield stress. Okay. So if we go through and we determine that we have a stress block, right? We looked at our drill stem or our propeller shaft, and we determined that we had a compressive stress, right, due to either the working in the fluid or drilling a hole in the earth. We had a compressive stress of 12 KSI acting on these shafts. And based on the power associated with either the drill rig, maybe it has 600 horsepower, right? And it's twisting this drill at 600 RPM. You could go through and figure out what's the torque that they're applying based on the torque and the geometric properties of the drill or the propeller. You could go back through and figure out the shear stress, right? We'd figure out that this shear stress in our case was 8 KSI. Again, we have our coordinate faces, say X to the right, Y upward. And we were designing this drill stem, and for us to sleep at night, I want to put a factor of safety of 2.5 on it, okay? And I not only want to put a factor of safety of 2.5, but I also don't want to put that factor of safety on an ultimate stress, because if they do exceed the factor of safety, I don't want whoever exceeded it, when it gets exceeded, that the shaft just shatters, right, or breaks. I'd rather than exceed it and they go too far and say it starts yielding or the bar starts twisting and doesn't actually fracture. So I'm going to say we're going to use a factor of safety equal to 2.5. So what does that mean? Well, that means we need to determine some of our allowable stresses. Well, our allowable stresses is our failure stress divided by our factor of safety. In this case, I'm designating the failure stress as being the yield stress. So we have 36 KSI over 2.5, so we get an allowable stress of 14.4 KSI. Same with our yield. 21.6 was our yield shear stress. 21.6 divided by 2.5, well, that's 8.6 KSI. So we figure out our stress state, we figure out our allowable stresses, we figured out our stresses based on that initial stress state, and now we can relate them, right? So we say our normal stress is 12 KSI, we know that. Well, that's less than 14.4 KSI. Our normal stress is okay, right? We've got more capacity, right? Our allowable stress is higher than our demand. 14.4 is greater than 12. If we look at our shear stress, right, it was 8 KSI. Well, that's less than 8.6 KSI. We're okay, right? Does that seem right to everybody? We good there? Okay. This isn't the end though, right? We gotta check our max stresses, right? And as we've been going through Moore's circle, there's a good chance that even though we found this initial stress state based on our imposed loading, that the combination of our shear stress and normal stresses will result in these principal stresses and maximum shear stresses at a plane that's not oriented within the axis of the shaft, right? We're gonna have to cut it at some angle. And when we cut it at some angle, we're gonna have different stresses, right? So our max stress may not be at initial stress orientation. Well, how do we figure that out? Well, we go through another Moore's circle exercise, right? Again, if we draw a circle, which you guys are getting so good at, I bet you bought, what is it, a protractor or a compass? Compass. I always get those messed up. All right, so we have our two coordinates. Positive shear downward, which is counterclockwise, positive. We've got clockwise, we've got positive normal stress to the right, negative to the left. Okay, we're gonna plot our 2 points. Well, if we look at our two faces of our initial stress state that we developed, right? X face and Y face. X face, we have 0 normal stress and 8 KSI of shear stress. So we're gonna be on our y-axis, and we're going to actually be above the x-axis or on the negative side because those shear stresses are clockwise, right? And then we know we have a compressive stress of 12 KSI, so we're actually down here, something like that. Draw this really nice straight line. Draw this really nice circle once I scribble something terrible. Oh, that ain't bad. Wow.
His is a lot better.
Yeah, his is a lot better than yours. So we have our coordinates, right? We just said that this is our x coordinate, so our 0, -8. Right. -8, we're above the x-axis. That's our x face because we have 0 normal stress. We have this 8 KSI of shear stress, and it acts in the clockwise direction, so it's negative, it's up on the top. If we look at our coordinates for the y face, well, we have -12, 8, right? Positive shear, we're on the bottom side, but now we have this compressive normal stress of 12 KSI, so we're down there, that's our coordinate. We can figure out our center. Well, in this case, it's -6, 0, right? It's the average stress between 0 and -12. Right, C.
For our y, would it be a -8?
For y? No, because this is positive shear. So it's 0, -8 on the top side. So our center is our average, or plus -12 over 2 is -6, right? Our radius, well, that would be the two components, right? Say this is our adjacent and our opposite. Our adjacent leg is our -6, right? So -6 squared plus our opposite leg, well, that's -8 squared, square root all of that. We get a radius of 10 KSI. Well, if we're looking for our maximum shear stress and our maximum in-plane, or our maximum normal stresses, right, which are our principal stresses, those principal or max stresses are the center plus the radius. In that case, we have -6 plus 10. that is 4 KSI. We also have our minimum principal stress, or sigma P2. It's the center minus the radius. So we get -6 minus 10. Well, that is 16 KSI. And we know that our radius is our maximum in plane shear stress, right? And that equals 10 KSI. If you were to analyze this drill stem or this propeller and related its computed stresses, right, based on the stress state, and you would have came up with the shaft being okay, it would have been wrong, right? Now if we look at this, the actual maximum stresses in this thing, right, sigma P2 is actually greater than our allowable stress. Right, we had 14.4 KSI was our allowable. We actually have a orientation or a plane in that shaft where we're going to have 16 KSI in compression, which is beyond our allowable. So that's no good. Then we have our maximum shear stress. Well, that's also greater than our allowable shear stress we calculated, right? We have 10 KSI of shear stress at a certain orientation. Well, that's greater than our allowable 8.6 that we calculated. So that's no good, right? So if you stopped up above, you could have made a very bad mistake, right? Fortunately, okay, it's unfortunate but fortunate, factors of safety have saved more lives than we'll ever know, right? Because originally, this really doesn't yield till 36. And so when we're saying our normal stress is 16 KSI, we're still half, right? Half, less than half of our yield stress of our material. So even though somebody probably has or will in the future stop here in their analysis, hopefully the factor of safety will overcome that. But that's not a recommendation either, right? It doesn't say that you can just cut corners like, oh, 2.5 will cover it. Good, it's good. But I'm just telling you how scary it is in real world that that shit happens. And fortunately, factors of safety do kind of pick up the slack. Did you have something?
Yeah, I was wondering if there's like a standard for choosing what your factor of safety should be.
For sure. That's where design codes come into play. So factors of safety are driven a lot by our ability to properly analyze and properly determine like both capacity and demand. So, I mean, if it's something as simple as like, I could take civil engineering into account, right? If it's an I-beam, so it's something like this, like a wide flange section, okay? Norm Asbjornson Hall has tons of them, okay? And they're spanning between 2 columns. Okay? When we design the flexural capacity of this, we use a factor of safety of like 1.67. But when we design the connection of this element to its column, it's upwards of anywhere from 2.5 to 5, depending on what that connection's doing. Is that connection just carrying this gravity beam, or does this beam play some bigger role in the overall capacity of the building? So if it's keeping the building from falling down in a windstorm or an earthquake, then we're going to use factors of safety that are a lot higher, right? But if it's just there to pick you and I up and transfer our load to the column, then it's probably in the 2.5 range, 2.67, somewhere in there, okay? In the end, it's just an educated guess. That's all we are. It's very good educated guessers, right? We can't accurately analyze anything, right? We don't know exactly how things got milled, how the molecules are all there, exactly what its yield stress is going to be. We can't exactly assess all of us in this room and the loading that it's going to see in its lifetime, right? So we're making all of these assumptions, and over the course of making all of those assumptions, we have to evaluate, well, how close do we feel like we have come to the real solution? And if we feel really good about it, we're going to use a lower factor of safety, right? The airline industry is a big example of that, right? If you used a factor of safety of 5 to create an airplane, they wouldn't be efficient enough to get off the ground. right? So then you end up refining that analysis, feeling really good about the loads you impose and the analysis methods you use to calculate capacities, and you get the factor of safety down to like 1.5. You know? So in this case, though, if we were looking at this drill stem or this propeller shaft, right, we got to the conclusion that, shit, it's overstressed, I don't feel good about it, right? You could do a number of things. We could use a 514 plate, which has a yield stress of 100 KSI. Or you could go back and we could change the geometric properties, right? We could change our polar moment of inertia, right? Which is a function of our radius, right? In order to reduce the stress in the shaft, right? Make it a larger diameter. If we make it a larger diameter, we're also increasing the area. So if we increase the denominator in those two equations, we're going to decrease the perceived stress in the shaft, right? In our drill stem or our propeller shaft. So as designers, we'd have to go back through, right? It's iterative, and that is design. Okay, that's it for stress transformations. Lucky for you guys, we're behind. And honestly, I don't think it's worth it. But we just went through a huge exercise on Moore's circle, right? And stress. In order to have stress based on, we look through tensile testing, right? And we have this idea of modulus of elasticity, which is the slope of that line, right? Our linear elastic line. Well, our stress is related to strain based on that modulus of elasticity, right? So in order to have stress, we have to have strain, right? Deformation. And so you can go through a whole exercise of a Moore's circle that's geared towards strains, right? So we can transform strains at any given cross-section and orientation of the same block, okay? There's a whole chapter on it. It's chapter 13, I believe. But we're gonna skip that. But just know that it's there, right? In order to have stress, we have to have deformations, okay? And if stresses change at any given orientation, that means our strains change too, right? The deformations that we see, if we were to slice our shaft at different angles, right? It's gonna see different stresses, different strains, right? So just know those are there. But I'd say stresses are the most critical portion because we don't deal with, at least for axial loads, because you don't deal with a whole lot of deformation. Okay, that's it. You guys don't want 315 stuff. Now this is when I get to figure out how much did you retain from Chris Allen. Okay? You retained everything, I assume, right? It's just right at the tip of your fingers. You're just ready. You love shear and moment diagrams, beams, right? Well, we're going to start jumping into beams or flexural analysis. That's kind of our last component, right? When we talked about breaking down mechanics, we kind of have axial demands. We've gone through axial loading. We've gone through torsion, right? And now we have bending. And when you capture those three and you understand those three, you've really captured most of the planet, okay? All right, you'd be the king of the planet, okay? Or queen of the planet, leader of the planet, whatever, all right? Equilibrium of beams, chapter 7, right? This should be I think it was 203. I'll add a couple question marks, okay? We'll see. So when we jump into flexure and we jump into beams, right? Beams are super common. Obviously, I assume all of you understand what a beam is. You guys have gone through shear moment diagrams, right? They're everywhere. They're everywhere, right? What is a beam? Well, it's, like I just said, one of the most common. Important. Components. Used in structural and mechanical applications. right? We could define them. Usually they're long, straight, prismatic members that support loads perpendicular to the, wow, this is long, longitudinal axis of our member, right? So beam, it was spanning from this lectern to that whatever cabinet over there, okay? It's going to be supporting loads that are transverse to the axis of the member, right? So vertical loads in that sense, okay? Those loads or forces are resisted by a combination of shear forces and moments, right? So we have these internal forces that are resisting these external forces, okay? And they come in the variety of shear forces and moments, right? Internal moments. And we have external forces, okay? So when we talk about beams, okay, we largely idealize support conditions for beams into kind of three categories. Okay, the first one, you guys have seen a lot, right, is the pin connection. So pin connection, if we looked at the reactions based on a pin connection, right, we have a vertical and horizontal reaction. Essentially, we have translational fixity, right? The beam can't go anywhere vertically, horizontally, in and out of the page, right, if it was pinned in the z-axis, okay? But it can rotate, right? There's no rotational stiffness. It's just that, a pin, okay? Good old teeter-totter. Then we have our roller support. Well, our roller support is similar to our pin, and then it has no rotational stiffness, right? It's not going to impose any restraint to the rotation of our beam at this point. But instead of a pin, instead of how the pin fixes our beam translationally in all directions, right? Now it's only going to be in the vertical sense, right? The beam can't move up or down, but it can slide horizontally. Next one is our fixed case, right? This is where we fix both translation and rotation, right? So we get a moment and we get two reactions, right? A horizontal reaction and a vertical reaction. Okay. And the depictions below this are an analogy to steel framing, right? Structural steel framing, and how we get this in the real world. Okay, so in order to get a fixed moment connection, okay, if you're driving around town and you see a steel building going up, okay, if it is mostly welded or there is some sort of element that's connecting the top and bottom of the beam to a column as well as the middle, like the web, right? The middle of the web being something that is translating our shear force, right? And then our flanges are transmitting our rotation, right? Our flexure forces. Whereas if we go to a roller, right, we're not going to see, if you saw a real roller in the real world, okay, out there in, where's the steel building? Whole Foods I was looking at. They're starting to put in, I'm a nerd for that stuff. Okay? They're starting to put in, they did precast panels over there too. Cool shit, right? Missoula precast. It is cool, right? Concrete is a terrible building material. It's not a terrible building material. I don't like it very much. but it's not very good in tension, right? It's a ceramic, essentially, like glass, okay? So it's very good in compression, but very bad in tension. So we end up putting steel in it, which is the most beautiful building material known to man, or humanity, okay? Love this, very, very simple. The reason why I love this, I'm diverging here, but this material, like, follows mechanics, right? Everything that you're learning in this class dives right into the design of steel, okay? Whereas concrete, it goes out the window. They do a bunch of tests, and then they best fit a line and say, well, shit, it's probably close to this. We're gonna do it this way, okay? And so with pre-stress, though, what you do is you put a bunch of steel in the concrete, but in order to get the capacity out of it, you end up squishing the concrete, right? Because it's bad in tension, so you never want it to go into tension. So what they do is they create these big, long beds, okay? They put tendons in them that they stress, pour the pad, cut the tendons. The stress that was in the steel rods, right? We had them in tension, now transfers into this steel or concrete wall panel, and it squishes it, okay? So we preemptively compress it so that it tries to stay in compression all the time. Minimizes cracks, increases capacity. So now where you had, say, walls that were 16 inches wide, you can get down to like 4 or 5 inches thick, okay? It's like super thin. It's kind of scary. It's actually really scary. Okay, diverged for quite a while there. All right, so if you were to look at this, Whole Foods, I think they're doing some steel framing, right? So they got this beam column connection. In order to get a roller, what they do is now they're only attaching to the web, right? That's where we transfer all of our shear, which we'll dive into that here soon, okay? No flange connections. And then the connections that we make a lot of times in structural steel is with what we call shear tabs or knife plates, where essentially you drill holes and you bolt it, okay? Well, we slot those holes, so it allows the beam to move in and out, okay? So that would be our roller, right? Analogy of a roller. Then the pin side, well, we bolt the thing, okay? Bolt the web to the column. But we gotta be careful that we don't create too much rotational fixity there, right? Because if you add enough components at that angle, they're essentially showing us an angle, right? If this angle becomes too thick and too strong and too stiff, right, it's going to restrain this beam from rotating. And if we originally assumed it acted as a pin, well, that's going to screw up all of our analysis, right? So we got to think about that when we're implementing our designs, right? Making sure that our assumptions we made, which are just that, like I said, this is an educated guess. So we're making the assumption it's a pin, that when we actually design it and put pencil to paper, right, and actually build it, we think about those as well. Okay. Stiffness attracts load. Okay. All right. As you learned in 203, is it 203 or 205? Whatever. Okay. Keep going back to 205. We have determinate and indeterminate systems. We all know what that is now, right? We've gone through those for both torsional and axial systems. Right? We really have 3 equations of equilibrium. And I cannot spell equilibrium. Okay, I'm going to try. Right? And those are some of the forces in the x, some of the forces in the y. Because we're working on a plane, right? We're not going to deal with out of plane, so don't worry about our sum of the forces in the z direction. And then we have a sum of the moment equation, right? And we know that all of those have to equal 0. Well, we know the basis that if our unknowns are greater than 3, it's indeterminate, right? Right? If we do example, if we have 4, that's first degree, right? Indeterminate, right? If we had 4 unknowns, we've got 1 additional unknown, then we have equations for equilibrium. So that means we're first degree indeterminate. And you guys have already solved some of those first degree indeterminate systems for axial as well as torsional systems, right? They were super easy. We just blew right through them. Everyone crushed it, okay? In beams, we have a bunch of different loading types, right? As I mentioned, we're talking about loads that are typically perpendicular, right, or transverse to the axis of a member, okay? So they can come in the form of a concentrated load. It's like you or I walking around. Uniformly distributed load, that's like the carpet on the floor, right? We've got a linearly distributed load, and I'm all talking about civil engineering because I think that's better, but snow loads, okay, haven't quite got enough snow yet, but snow loads, drifts are linearly distributed loads, okay? Right? So like the gyms that collapse, they had a big drift associated with it versus the center gym, which was higher, right? Wind load comes up, or wind comes up, blows the snow against that wall, right? Parapet walls are another one that you get this increase in snow load. So you get this linearly distributed load that gets attached to your building just inside the parapet. And then you have a concentrated moment, right? Maybe you had, maybe you're someone that has a flagpole on the top of their building, right? The flagpole gets pushed on by wind. That wind's going to impose a moment on your beam, right? So you can have a concentrated moment as well. As I mentioned, right, these external forces are resisted by internal forces, right? And these internal forces transfer these loads out to our reactions, right? And then take it on further into the building, the structure, down to the foundation, right? So then we just say earth takes hold from there, right? So we have these internal forces. They come from our external loads. So if we look at this beam configuration, right, we have a simply supported beam with an overhang, right, points A, B, and C. We have some point loads and and a uniformly distributed load, okay? So those are our external loads. And then we have our internal forces, right, that are resisting those external loads, those internal forces and external reactions. These all come back to our equilibrium equation, right? In free body diagrams, right? We cut this beam. We have some external forces, we have some unknown reactions, okay? We have some internal forces. We can then use our equation of equilibrium to solve for some of our unknowns, right? As always, we have sign convention, okay? These internal forces, for instance, right? This shear in this moment that we're assuming are acting internally to the beam, right? You guys have done lots of shear moment diagrams. We're gonna go through those here. But they have sign convention, okay? Up on the left, down on the right, okay? If you took a slice out of your beam and it rotated clockwise, okay? If it rotates clockwise, we assume that that's positive shear, right? So up on the left side of the beam, down on the right side. Negative shear, well, obviously rotates it the other way, counterclockwise. Do not try and connect this back to Moore's circle, okay? This is exactly opposite of shear stress in Moore's circle, right? Counterclockwise was positive, which was the bottom side. Well, clockwise is positive, counterclockwise, okay? Then with positive moments and negative moments, right? You create a smiley face, it's positive, right? You smile, it's positive, hopefully. You frown, it's negative. Maybe those aren't universal, maybe you work opposite, but that's the way I think about it, okay? And Friday, we'll start going through shear and moment diagrams. Don't forget the quiz.